a card, a horizontal sheet, 2 wires poke through. There's a current in wire A shown. Alright. Draw 4 field lines of PQRS to represent the magnetic field due to current A. Oh, okay, this is basically the same thing like just now. Did they copy paste all this past year? Nothing new to us. Okay, never mind, we draw. So we know they're going to be in concentric circles. First few ones, very close to each other. As they get further, you make sure the separation kind of increase lah, okay? Then the next one is much bigger. There, something like that. And use your thumb, right hand rule to check. Your thumb should be pointing upwards because current is flowing there. So all your fingers should curl around this way. Anti-clockwise. The mark scheme is exactly the same, which is, okay, if you draw more than 3 circles, concentric circles, okay, liao lah, M1. If your separation is increasing, means the circles are getting further and further apart, then also 1 mark. And lastly, your direction correct or not, anti-clockwise, the purple color arrows. If that one's correct, B1 mark. 1, 2, 3. Okay! Ayo, this one hopefully you can close your eyes and draw already by now. Practice more if you're not sure how to draw this one. Okay, now, a direct current is now passed through wire B in the same direction as wire A. Oh, means they are both parallel and current is flowing in the same direction for both of them. The current in B is larger than the current in wire A, kind of like just now lah. So in the figure, draw an arrow to show the direction of the force on wire B due to magnetic field produced by the current in wire A. So we need to draw an arrow on B. Let's first add a current. So they say current in the same direction. So that's why they're both going up. Oh, I just follow the first one only ma. Then we gotta think of where is the force going to be pointing. You gotta think about what happens, let's say here. So if we think about the magnetic flux density, the arrows that we are drawing, where is it pointing at the location at wire B? At the highlighted spot right there, over there, okay, I draw another highlight lah. Okay, I take it out. The magnetic field is kind of pointing upwards lah. Right, that is the B. Current is out and vertical. Like that. So where would the force be pointing? So let's do our finger. So I is going to be your middle finger pointing upwards. B is your pointing finger. Where will the thumb be? So rotate your hand. Thumb should be pointing to the left. That's your force. Okay, if you feel like I don't know how to see 3D diagram, never mind, I redraw for you. So if you want to look at the side view, like you put your eye here and you look along the magnetic field, then you would see magnetic field going away from you into the page or into my screen. Current is upwards, like that, and your thumb should be pointing to the left. It's kind of like you use your pointing finger, you point at this X right here, so you point right at it. How do like that? You point like that in. Point, middle finger up, and then your thumb. So for those of you looking in the video, it'll be something like this. Right? So your force should be pointing to the left. So on your diagram, make sure you draw a nice big F here. Okay, so this is that. This is right here lah, side view. Okay, so that one is 1 mark. If you draw in that direction, okay now. In fact, both of these wires will experience a force on by each other. So wire A pull wire B. Wire B also pull wire A. They pull each other together. Wow, very nice. Okay. Wire A also experience a force. Yup, we just drew this one here. State and explain which wire will experience the larger force. Is this a troll question? Just now we already saw the answer, right? We talked about this. Which one got larger force? The force will be the same, miss. Why they say which one will have larger force? Troll question. So sneaky. State and explain. So, none of them, they'll be the same force. So all you can say is, the force, I'm going to shortcut here because there's a little bit of space only. So force is proportional to the product of currents, IA, IB, like what we did just now, but right in a full sentence. Force is proportional to IA, IB, and So both forces are equal in magnitude. It's just a product of current. If your current bigger, then the whole force is bigger. Force on both sides. So both forces are equal in magnitude and opposite in direction. Opposite direction. Newton's third law, might as well write there. Drop a name inside there. Hashtag or @Newton. So sure, Newton's third law. 2 marks. The first one is you talk about the proportionality. This thing. Did you know that is a thing? The equation, the relationship. And of course, you talk about forces are equal, or Newton's third law, and hence forces are equal. Then there is A1. Some of you may also just say Newton's third law, and then that could be another mark that replaces the M1 mark. Can also but we only need 2 marks, right? Okay. So this one is still the same as the previous question. Now this last part is new. The direct current in the wire now changed now, becomes sinusoidal alternating current. What is this? We haven't learned this yet, but sinusoidal AC current is basically current that can change up and down like a sine curve. The currents are in phase. Means both current will either be up together or they'll be down together at the same time. Up, up, down, down. So that like that lah. Okay. Upwards, downwards, upwards, downwards. In phase. Describe the variation of the force experienced by B. Let's go back to the diagram a bit. Variation of the force experienced by B. Okay, so how to think of this? When you have sinusoidal current, how will the current graph actually look like? Come, let's draw down here. So when we say sinusoidal, it looks like this. You have a current. Over time, a certain frequency, it will oscillate. Change direction. Okay. So that means at some points, these 2 wires will be upwards. And that is this positive part. Then some later point, it will also go into negative part. Means the current is now flowing downwards together. But despite that, what's the force like? They're still attracting. As long as they're pointing together, you will still have an attractive force together. Force. So also together. Force. But this force will also oscillate. Sometimes it's big, sometimes it's small. It really depends. So when is the force the largest and when is the force the smallest? Think back to your equation. F equals to BIL. How to use F equals BIL? F equals to BIL sine theta. Now our I here is oscillating or sinusoidal, alternating. That means our force also is oscillating. Means sometimes it's very strong, sometimes very weak. Sometimes very strong, sometimes very weak. Because no force, no current, then cannot have force. So if I draw the graph of force against time, when there is no current, there is no force. Here, no current, no force. So it should pass through all these points. But you see, the forces are always pointing towards each other. They never change direction. So it's always in the positive side of the graph. So it's something like this. Something like that, okay? Roughly. So you have a maximum force up here. F max. Then you have no force down there. 0. So that's how we can describe. How are we going to describe this variation in a sinusoidal graph? So you can, firstly, you can mention that it's always in the same direction. They're always attracting each other. You're looking at the force on wire B, right? So this is AB, AB. So wire B will always experience a force to the left, no change direction. So let's say that first. So the force on B is always in the same direction, no matter which direction your current has alternated for both of these wires. Force on B is always in the same direction. What else shall we say? The nature of up and down, up and down. Okay, so force B always in the same direction. And this force will vary, right? From where to where? From 0 to maximum. This is also kind of like a sinusoidal variation. Sinusoidal variation. Okay, can lah. This is how you can describe, basically describing the graph of the nature of what's happening here. So the first is you talk about force always in the same direction, no change in direction. You see here, this force, always pointing to the left. So that is B1 mark. Then if you talk about if change from 0 to some maximum value, like a sinusoidal curve, based on the sinusoidal function, so that one is this part. Another 1 mark. So actually B1 lah. Okay, B2 for both of it. Okay, so that is how you can think of AC wires. We will learn more about AC in a future chapter. But before I close off this video, one quick brainstorm. If we are doing DC, how would you connect these two wires such that you can hook it up in the circuit and you have either together or not together? So one way is you can connect them in series. Let's try this. What if I say, I put a battery here, then I connect the wire. How to connect? Maybe wire come down here, first wire go up here, then go back to battery. So the wires that I want to play around with is going to be in these two sections lah. Okay, here. Current, down and up. Ooh, you see this? So if we zoom in on these two wires, this is what we call connecting in series. So when you connect a wire in series means the current only can flow in one path, right? Then you have two parallel wires in opposite direction, like that. Okay lah, maybe don't short the circuit, put some resistor here to slow down the current. If not, the current is super big, man. Okay, so this is how you can actually do this experiment in real life. You connect two wires in series. What about if you want them in the same direction, then you try connect them in parallel. So, like this, and then you split, create a junction, and rejoin at the bottom. So where will the current flow? Current flow out of the battery, then come down here, then combine and go out, go back. So if you look at this main part, it's going down, and where is it? Here, also going down. So, if you want both current to be in the same direction, you can connect a circuit like this if you want to do an experiment to set up to see the attraction between these two wires. Okay, so this is connected in parallel. Two wires connected in parallel. Then you have current flowing in the same direction. Can Okay, so that is all for this section, and that is the end of 22.2. Woo! Force on conductors is finally finished. So in the next part, we will be looking at force on particles now. So not so much of wire and current, but now positive charge, negative charge, spin here, spin there, go everywhere. Okay, so that's all for this video. I will see you in the next one. See you about force on particles.